All right, so in this module, we're going to talk about the second part of free energy, and that would be entropy. So you can think of entropy as a measure of disorder. So that's, I think, how most people kind of like to describe entropy to a typical audience. We're going to define it a little bit more specifically in terms of temperature and so forth. So, and this is kind of we consider this what's called a macroscopic approach. We can define it in terms of heat. So entropy is defined in that way by the heat absorbed. So similar to how we did with enthalpy, in a reversible process. And that's then divided by temperature. So heat absorbed divided by temperature. So we can write that as the change in entropy, so the small amount of entropy is defined as that quantity of heat, delta Q, and we call that reversible for the because it's a reversible process, and it's divided by temperature. All right, so that's how we, in traditional thermodynamic classes, that's how we define enthalpy. A lot of times in materials, though, we like to look at it on the sort of macroscopic domain. Because a lot of times we're thinking about particles or ions or electrons. And so in that case, we can relate entropy with what's called the Boltzmann's equation. So the Boltzmann's equation, it incorporates what's known as a probabilistic model, probabilistic approach. And so that equation, that Boltzmann's equation, is entropy, S, is equal to K times the natural log of omega sub beta. So this is entropy, right? And so this has units of joule per K. This K is a constant, and it's known as Boltzmann's constant for obvious reasons. And so that's equal to 1.38 times 10 to the minus 23 joules per Kelvin. And then we have this last term, which is known as the total, which is the total, defined as the total number of different configurations in which the system can be arranged at a constant energy. So this is just another way of defining entropy, and we do it by considering all the different configurations of the system. And so we'll take a look at this in a little bit more depth as well. But first, what I want to do is just kind of go over entropy and the different types that we can have, because there's not just one type of entropy. So the first that we look at is called configurational. configurational. And so this is related to the number of configurations of the system. And so this can be directly thought of in terms of the Boltzmann's equation. Total number, the number of configurations, let me finish this, in which we can place atoms or defects as well, can be arranged on a given number of sites. So having atoms and defects like vacancies, how can we arrange that over the total number of lattice sites? And that's known as the configurational entropy. We can also have thermal. And so in this case, again, we typically think of the classic thermodynamic definition, but we can also think about it in terms of Boltzmann equation. And this is where that omega term is the number of possible different configurations in which particles can be arranged over existing energy states. So instead of thinking about arrangements of lattice sites, here we're thinking about particles in different energy sites, which would then be tied, obviously, to thermal energy. So those are the two main these are the two main types that we talk about, but there are other types of entropy as well. There's electronic. So basically, probability of looking at electrons in various sites, energy states. There's also magnetic entropy. There can be dielectric entropy, and there's a number of others as well. But we're going to mainly focus on the first two and look at different sites. So atoms and defects that you can place on lattice sites, and also particles and different energy arrangements. And so those are the two that we're going to focus on. All right, so let's go ahead and talk about the first type, configurational entropy. All right, so again, this was associated with atomic disorder. So what we're going to do is we're going to kind of look at this in a small system. So let's consider that we have a simple system, and we have n number of point defects, so or vacancies. And we have capital N atoms, and those are distributed over a total number of sites equal to lowercase n plus capital N. All right, so we have n point defects or vacancies, and then capital N atoms, and they're distributed over a total number of sites, and that's just the sum of those two numbers. And so the total number of configurations that we can have for the Boltzmann equation is that omega term, and that's going to be equal to n plus capital N, and then factorial over n factorial capital N factorial. So this is how we describe the total number of different configurations possible for this simple system, talking about atomic disorder. All right. So when we're looking at these systems, they are simple systems, but you got to keep in mind the numbers, right? So for a typical amount of material, we often think about moles. So that's 10 to the 23 atoms. And so because of those large numbers, it's often difficult to calculate factorials of very large numbers. And so if you want to, try this out, just use your calculator and start small and then build your way up and see that it's actually quite small in which you can calculate these factorials. So we need a different way to calculate these for large systems like we're dealing with in materials. So what we use is Stirling's approximation. And this says that the natural log of a factorial of x is equal to x natural log of x minus x. So we're basically approximating this factorial by this expression here. So what that gives us is it allows us to basically take this expression and the configuration definition up here and come up with the Boltzmann's equation for configurational entropy for this simple system. So we have minus k, and then that's going to be times n, capital N, natural log of n over n plus n, plus lowercase n times natural log of lowercase n over n plus capital N. So this gives us an expression for being able to calculate the configurational entropy at constant energy for this simple system of vacancies and atoms using this approximation and looking at the total number of distributions. And I'll kind of maybe bring you back to something you might have talked about in MSE 351 thermo. You might have seen this expression. So you might have seen the configurational entropy is equal to minus R XA natural log XA plus XB natural log XB, right? So you might have seen this. This is actually the configurational entropy of an ideal solution of two components. And so you're going to notice that this looks very familiar with this. So whether we're talking about vacancies and atom sites, it's very similar to, almost identical to, the configurational entropy of an ideal solution. So this is for ideal solution. All right, so that's just something you might have seen before.